Hello, and welcome to Matrix Addition and Scalar Multiplication. These are the notes for when I taught this as a lecture class in a face-to-face classroom, but I'm using the exact same notes to record for online classes and those that miss the lectures. So let's start with some definitions and an option for a pen. Let's start with the definition of a matrix. An M by N matrix A is a rectangular array of real numbers with m rows and n columns. All right, m rows and n columns. We refer to the m and the n as the dimensions of the matrix. All right, so the number of rows and the number of columns, very important. Usually, most things in math are alphabetical. Rows and columns, not. So matrices are the first kind of thing that kind of screws up, but it's all right. Rows and then columns. Fewer letters and then more, however you need to remember that. Let's look at some notation. We generally use capital letters, A, B, C, and so on. You know the letters. For the names of matrices. For example, the matrix A, it's a rectangular array. It has these brackets on the side. Yep, they're brackets. I call them square parentheses or square brackets, usually. The first row consists of 1, -5, 2, and the second row consists of -11, 8, 57. Notice there are 2 rows and 3 columns, so this is a 2 by 3 matrix. The matrix B, on the other hand, still a rectangular array enclosed by our little matrix notation here. First row, 3, -10. Second row, 0, 5. Third row, -2, 7. So it has 3 rows and only 2 columns, 3 by 2 matrix. So the dimensions are different, even though they both have 6 entries. It's not all about the total, it's about how they're arranged. Okay? So what is an entry? The numbers that appear in a matrix are called its entries. We refer to the entries by the lowercase of the matrix name, along with 2 subscripts, I, J, where the I refers to the row number and J is the column number. So for example, in the matrices above, A22 in the matrix for A, row 2, column 2 is 8. And B21 in the matrix for B, row 2, column 1 is a 0. If I wanted to find A11, I'd go to the matrix for A, row 1, column 1, that answer is a 1. That looks like a parenthesis. That's what I first saw when I came here. So I'm going to make that into a better one. If I want to find B33, and I don't really read it as B33. I don't read it as A11. It's B33 because it's the third row, the third column. Well, B doesn't have a third column, so this does not exist. So watch for that, all right? Make sure that things that they're asking you for are actually there. All right, let's talk about matrix equality. We say that 2 matrices, A and B, are equal if they have the same dimensions and corresponding entries are equal. Now, this one's kind of written all over, but if matrix A is the matrix 1, 5, second row, X8, and that's usually how I'll say a matrix out loud. I'll say the first row and then let you know when the next row starts. B is the matrix 1, Y plus 2, second row, -3, 8. We want to find the values of the variables. Well, the first thing we check is that A is 2 rows and 2 columns. B is 2 rows and 2 columns. So these are both 2 by 2 matrices, so I know they have the same dimensions. Well, that's ridiculous. This should assume that A is equal to B. And I never say that anywhere in the example. I apologize for that. But we can see the row 1, column 1 matches up. Row 2, column 2 matches up. That tells me that I need to have row 2, column 1, X match with row 2, column 1, -3. So X must be -3. And row 1, column 2, 5 has to match with row 1, column 2 of Y plus 2. So if 5 is equal to Y plus 2, I can subtract 2 from each side, and Y will equal 3. I found the values of the variables. I apologize I didn't put in the important assumption that A equals B. A matrix with a single row is called a row matrix or row vector. That's not how it is at all. Let me fix that. Hopefully. No? Okay. Come over here. Maybe we'll fix that. No, we don't want to fix anything. All right. We'll just ignore that then. A row matrix might be 1, 0, 3. Whereas a column matrix is a matrix with a single column. Maybe it's X, Y, Z. The X just got sloppy, but the Z will always be crossed because my 2's and my Z's look very similar, so my Z's will be crossed. A square matrix is a matrix with the same number of rows as columns and is called a square matrix. So anytime M equals N, we have a square matrix. If the row is a 1, or if the column is 1, we also have a special matrix called a row or column matrix. All right, now let's talk about how to add and subtract these two things. First of all, the most important rules. Two matrices can be added or subtracted if and only if they have the same dimensions. So first thing we always check, always note in any matrix is what are its dimensions. Now that they have the same dimensions, to add or subtract two matrices, we add or subtract the corresponding entries. Okay, that's what we do. Now here's the math version of that. If A and B are both m by n matrices, then A plus B and A minus B are m by n matrices whose entries are given by the sum entry is taken from that entry of A plus the corresponding entry of B. So these words, my words, and the mathy rules that go along with it, I'm here to help you interpret your textbook. Okay, let's look at an example or two. We're going to let A be the matrix 1, 0, second row 0, 1, third row 1, 1. B is the matrix 12, negative 7, second row 5, 3, third row 11 and 2.3, don't forget that decimal. C is the matrix given by 2, 1, second row 1, negative 2, third row negative 1, 2. And we're supposed to find the following, A plus B. So I know that matrix A has 3 rows and 2 columns. I know that matrix B also has 3 rows and 2 columns. Since the dimensions are the same, in order to add them, I will add 1 plus 12 in row 1, column 1. I'll add 0 plus negative 7 in row 1, column 2. Similarly, 0 plus 5, 1 plus 3 fills out our row 2, and row 3 is 1 plus 11 and 1 plus 2.3. You will not need to show this answer on the homework. This is just for you, just for building your work. If you could look at 1 plus 12 and know it's a 13, go ahead, write the 13. 0 and negative 7 is negative 7. 0 plus 5 is 5. 1 plus 3 is 4. 1 plus 11 is 12. And 1 plus 2.3 is 3.3. So this is our answer matrix. On WebAssign, you might have some arrows involved in your answer. If you need a new column, push the green arrow on WebAssign and it'll give you another column. If you need a new row, maybe the answer only has a row vector or a row matrix. If you need a new row because your answer is bigger than what they give you, or less, right? It has arrows going both ways. So I can also take back a row. And similarly here, if I could draw it, we'll delete a column. You won't need that very often, but there's at least one problem where this shows up. I just don't happen to remember where it is. So I thought I'd tell you about it now in case it pops up in a later video. Okay, so as long as the answer matrix is the size you expect it to be, it's all good. If it's not the size you expect it to be, you can add rows or columns or adjust in whatever way you see fit on WebAssign. All right, so WebAssign has those notations. If I'm trying to find C minus B, I notice that C is also a 3 by 2. Since they're all 3 by 2s, I can do my addition and subtraction, no big deal. So I will take C first, 2, and then subtract B, 12. So 2 minus 12, 1 minus a negative 7, 1 minus 5, negative 2 minus 3, in the corresponding entries, negative 1 minus 11 in row 3, column 1, and finally 2 minus 2.3 in row 3, column 2. Do all the little arithmetics here. 2 minus 12 is a negative 10. 1 minus a negative 7, those two negatives come together and tell us to add, so that's a positive 8. 1 minus 5 is a negative 4, negative 2 minus 3 is negative 5, negative 1 minus 11 is negative 12, and finally, if I have 2 and I subtract 2.3, I have a negative 0.3 remaining. Okay, so adding and subtracting matrices plus a little WebAssign tip over here for you. Let's talk about scalar multiplication. Now this one got a little rowdy, as I was writing the notes, but I'm here to interpret it for you. Here we go. First of all, what is a scalar? Single value units are generally referred to as scalars in mathematics, as they are a scale factor, or an amount that we multiply by. All right, so a scale factor, if you see model cars in the store, it might have a 1 to 12, so a 1-inch part should normally be 12 inches, or a 1-inch part might be 12 feet, depending on their scale. When you see, okay, I have a vast array of movies I watch, but one that pops in my head because we watched it recently was, oh my goodness, Cher and Christina Aguilera. Moulin is not the Moulin Rouge, it's the other one. It's the, it's a form of dancing. Anyways, in that movie, they have a model of what's going to be built. Frequently, architects will do this. They'll build a model, scale model. It's called a scale model. I'm getting way off track here, like I'm in a classroom. It's just the amount that we multiply by. So a scalar multiplication is just multiplying a matrix by a number. That's it. We call it scalar multiplication. So if I want to multiply 3 times A, what I'm really going to do is I'm going to multiply 3 by every entry in the matrix A. And that's what this says. It's 3 times parentheses 1, 3 times parentheses 0. Second row, 3 times parentheses 0, 3 times parentheses with a 1. 3 times 1, and 3 times 1. So 3A happens to be the matrix 3, 0, second row, 0, 3, third row, 3, 3. But you see, we could also do linear combinations. We could do 2B minus 5C. So here, I take 2 times row 1, column 1 in B, minus 5 times row 1, column 1 in C. And I've done, I've written them separately. That's a 4, not a 9. 24 minus 10. So I did 2B. Still have my minus sign. I computed 5C just using my scalar multiplication. And then we do subtraction. 24 minus 10 is 14. Negative 14 minus 5 is negative 19. This is a negative 5.4. They're all sloppy, but they all go in that spot. All right, so addition, what is a matrix? All right, looking at 2 matrices are equal if they are the same size and their corresponding entries are equal. We can only add or subtract matrices of the same dimensions or same size. And a scalar multiplication is just multiplying every entry in a matrix by that real number value. Let's look at some properties of matrix addition and scalar multiplication overall. Now that we've seen examples, we'll put it in mathy terms. If A, B, and C are any m by n matrices, and if 0 is the 0 m by n matrix, I'm going to just write this here. I would call this my 0 2 by 2. It's just a matrix full of zeros that has this dimension. So in this case, in general, m by n, all the entries are 0. We have an associative law. It doesn't matter when you're adding three matrices, it doesn't matter which order you group them in. Commutative law. Whether you add A plus B or B plus A, it doesn't matter because addition is cool. Addition can go either way. Yeah, giggle. Additive identity law. If you add the 0 matrix to any matrix A, it's the same as adding 0 on the right or on the left. You just get the matrix A back again. Additive inverse law. If you multiply every entry in A by a -1 and then add it to the original matrix A, you'll get back to 0. That's saying 2 plus -2 is 0 in a fancy way because it's no longer 2, it's a whole matrix, but same idea. Distributive law in two ways. We could have a constant multiplied or a scalar. Let me use the right term. Scalar multiplied by A plus B. So we can multiply the scalar by A, multiply the scalar by B, and then add the matrices, or add the matrices and then multiply the result by the scalar. Similarly, if we have a sum of scalars multiplied by a matrix, that distributes as well. Our scalar unit, 1. Scalar unit, yes, scalar unit 1. If I multiply 1 times A, I get A back again, right? Because 1 times 3 is 3. 1 times 17.425 is 17.425. 1's awesome like that. And a scalar 0, if I choose to multiply a matrix A by a scalar of 0, it turns everything into 0. These are the formal properties that basically tell us adding matrices is awesome. Notice these are not subtraction signs in here. All right, be careful as you throw in your subtraction. Last fact I want to talk about real quick right here. If A is an m by n matrix, then its transpose, all right, it's a new term, is the n by m matrix obtained by writing its columns as rows. So the ith column of the original matrix becomes the ith row of the transpose. We denote the transpose of A by A with a capital T up above it. So if I have the A as a matrix 1, 2, 3, second row 4, 5, 6, third row 7, 8, 9, you can see I really reached out for a good example here. And I want to find its transpose. I'm going to take column 1, 1, 4, 7, and that becomes my new row 1. Right? It's columns as rows. So this first column, let me draw the right direction here. This first column is now my first row in the transpose. Second column, 2, 5, 8, is the second row of the transpose, 2, 5, 8. And the third row of the original matrix, 3, 6, 9. Original third column, I don't think I said that right. The original third column of matrix A becomes the new third row of A transpose, 3, 6, 9. Okay? Properties of the transpose. If A and B are m by n matrices, then if you want the transpose of a sum, you find the transposes and then add. If you have a scalar multiple and then of A and then a transpose, it's the same as finding the transpose and then the scalar multiple. And if you take a transpose and you transpose it, you get back to A, right? Because what's next? I'm going to take this column, 1, 2, 3, and I'm going to make it into a first row, 1, 2, 3. So the transpose of the transpose takes you back to A. We will not be finishing the lecture with some more examples from the worksheet. That's a lie I tell myself, when in reality, I'm probably tired of lecturing by this point. All right, that's it for this lecture. I might be making the future ones a little shorter so it doesn't feel like you're sitting in a classroom. Thanks for listening. Let me know if you have questions on the homework.